joint TVHS Center for Climate Change and Center for Atmospheric Science seminar by Dr. Nandini Ramesh. Dr. Nandini Ramesh did a bachelor's in physics from Stella Maris College in Madras. And during the time, she spent one summer at the Center for Oceanic Sciences to work with Professor Raghu Murthugude on El Nino. And from there, she went on to do a master's in Earth Physics from Australian National University. And then went to Columbia University for her doctoral work to work with Professor Mark Kane and Professor Richard Seeger on the predictability of tropical Pacific decadal variability. She has got many recognitions. She got a gold medal for her undergraduate PhD physics. She got a Dean's Fellowship from Columbia University. She's also NASA Earth and Space Science Fellowship. And she has published some very interesting papers related to global marine fisheries, Pacific decadal variability, and the persistent cool state of the Pacific Ocean. Now, the last topic is interesting because we are going through this cool state right now. The La Nina is still quite strong. So we are happy to now invite Dr. Nandini Ramesh to give a talk on the unexpected oceanic peak in the energy input to the atmosphere and its consequences for monsoon rainfall. Dr. Nandini.
Thank you. So thanks so much for having me. I was an intern at Chaos a long time ago, as Professor Srinivasan mentioned. So it's really nice to visit again, even though it's only virtual. I'm currently based at CSIRO, but most of this work was completed while I was a research fellow at the University of Sydney. And the work was initiated while I was a postdoc working with Bill Booth at UC Berkeley, who's my co-author on this paper. We also received funding and computational resources from the US Department of Energy for this work. I'm going to start with some background on why the net energy input to the atmosphere, which is the quantity that we're interested in this work, is important to explaining spatial patterns of rainfall, especially in the tropics. The study itself is in two parts. Part one is an analysis of the observed net energy input into the atmosphere, in which we find some surprising results. The primary one being that the global maximum of this quantity occurs over the northern Indian Ocean during boreal summer. We found that cloud radiative effects played an important role in this, and so in part two of the study, I'll show some experiments with a climate model in which we eliminated the effects of clouds over the tropics and examined how that impacted both the net energy input and the rainfall over Asia. We interpret our results using two different frameworks, and as I will show, this gives us consistent results in both frameworks. At the end, I'm going to summarize and outline a few of the interesting questions that this work has raised. The central quantity that we're interested in this study is the net energy input to the atmosphere, which I'm calling NEI. And that's made up of surface fluxes and top of the atmosphere fluxes. And the reason why this quantity is interesting goes back to a line of work from the 2000s. So several papers around that time showed that if you place an energy source in the atmosphere in one hemisphere, the ITCZ would shift towards that hemisphere of the energy source. On this slide, I have an example from Broccoli et al. 2006, but I should say that this was far from the only paper that dealt with this topic, and a few of the other key papers are listed at the bottom. So in this particular experiment that they performed, the authors added a meridionally asymmetric forcing at the surface so that the surface was supplying heat to the atmosphere in the southern hemisphere and removing heat from the atmosphere in the northern hemisphere. So this was in an idealized model. So here in the first image at the top, you can see that they had a perfectly symmetrical Hadley circulation. The contours are showing the stream function in their control run. And in the lower panel, where they imposed the heating and cooling, you can see that the northern hemisphere Hadley cell has expanded southwards in this experiment, which ends up placing the ITCZ to the south of the equator. So you can see that southward shift of the ITCZ very clearly in the picture on the right, which shows the precipitation anomaly field. Now that expansion of the Hadley cell in the northern hemisphere has the effect of increasing northward energy transport by the atmospheric circulation. So the figure in the middle shows this, where in the experiment, that is with the imposed asymmetry, that's shown by the red line, the northward energy transport is larger than in the control run, which is shown by the red line. So the circulation is responding to this asymmetry by adjusting the heat transport to balance out the asymmetry. And that idea has now been applied in a number of places, and it's quite familiar to many of us by now. We know that the ITCZ generally moves towards the warmer hemisphere. So this has been invoked to explain, for example, why the zonal mean annual mean ITCZ lies in the northern hemisphere, which is because of the uneven distribution of the continents between the two hemispheres. So the northern hemisphere is on average warmer, meaning that the ITCZ is pulled towards the northern hemisphere. It's also been able to explain how the ITCZ moves over the season. It always moves towards the summer hemisphere, which is warmer. And it's been invoked to explain several paleoclimatic studies as well. So while that concept has proven really useful and quite robust, it can only explain zonal mean changes. In a recent line of work, my co-author Bill Boos and his various co-authors have tried to expand this basic idea to try to explain regional and not just zonal mean precipitation patterns. So in this example, they looked at the Walker circulation, which is zonally oriented across the Indo-Pacific, rather than the meridional Hadley circulation. So they used El Nino and La Nina events as a test case to prove this concept. So let's start by focusing on the red lines in the figure. So here the two red lines show the zonal energy transport. So previously we were looking at the meridional energy transport, and now we're looking at the eastward energy transport. The Walker circulation expands and strengthens during La Nina events. So you can see that the dashed red line, which represents the La Nina events, transports more energy than the solid red line. And as a result, you can see that the longitude where the energy transport is crossing zero, so I've marked that with these yellow diamonds, shifts towards the east from El Nino, which has the weak Walker circulation, to La Nina, which has the strong Walker circulation. So that line is called the energy flux equator, or sometimes the energy flux prime meridian. And it's used to estimate by how much the precipitation should shift. So now moving on to the blue lines on the graph, which show precipitation. Again, the dashed line is showing La Nina and the solid line is showing El Nino. The centroid of precipitation, which is shown by the green dots, shifts by about 22 degrees. So from about 150 east under El Nino conditions to about 130 east under La Nina conditions. So that shift happens in the same direction as the energy flux equator and is also of a similar magnitude. So the flux equator shifted by 19 degrees and the precipitation centroid shifted by 22 degrees. So that longitudinal shift in the energy transport was a pretty good predictor of the corresponding shift in rainfall. Now that was again only in one dimension, so you lose all the meridional information by doing that, just as we were losing all the zonal information by looking at the Hadley cell earlier. So to get further with this basic idea of predicting rainfall shifts from the energy sinks and sources, they generalized this to two dimensions. They introduced a term that they called the energy flux potential, which is chi here. And the Laplacian of that quantity is equal to the divergence of the vertical integral of energy transport. So we're representing energy transport as the product of the moist static energy H and the velocity field U. Moist static energy is the sum of the latent heat energy, so that's LVQ, the thermal heat content, that's CPT, and the geopotential energy, which is GZ. So that accounts for the total energy content of the air. And we're looking at the vertical integral over the atmospheric column. Now, through the conservation of energy and mass, the divergence of the vertical integral of this quantity, that is the energy that's going in and out of the sides of the column, should be approximately equal to the amount of energy coming into and going out of the column at the bottom and top. That is the surface latent heat flux E, the surface sensible heat flux S, and the net radiative flux into the column R. So this quantity, the Laplacian of the flux potential, is roughly equal to the sum of vertical fluxes into the column, meaning that this represents sinks and sources of energy going into the atmospheric column. So going back to that El Nino example, here the contours are showing the Laplacian quantity, which has its largest magnitude over the area of the tropical Pacific that is usually supplying the most heat and moisture to the atmosphere during an El Nino event. And the arrows show that the circulation is acting to diverge energy away from that source region. They've also marked in red for El Nino and blue for La Nina the zero lines of energy transport in each of the horizontal dimensions. So they were able to show that using the changes in the sources and sinks of energy to the atmospheric column was one way to estimate the associated shifts in the precipitation field. Now, this was a very powerful result because that net energy input quantity is something that can be quite easily diagnosed in a model or in a reanalysis. So the terms that we would need to do this are the fluxes at the surface. So there are two radiative fluxes, which are shortwave and longwave, and the two turbulent fluxes, so latent and sensible heat flux. At the top of the atmosphere, we have incoming shortwave and outgoing longwave. Cloud cover interacts with the top of atmosphere part of the budget by blocking shortwave from coming in and blocking longwave from escaping to space. So since all of these terms are produced by reanalyses and models, we have all that we need to calculate that flux potential quantity from reanalyses. And that's where I'm going to start by looking at the global spatial pattern of the sources and sinks of energy going into the atmospheric column. So let's look at this quantity in a reanalysis product. I've set the sign convention such that positive values, shown in red, represent sources of energy going into the atmosphere. That is a net input into the atmosphere. And blue means that it's a sink of energy, that is energy is leaving the atmosphere. So the map shows the seasonal mean net energy input during boreal winter. And the most striking feature of this map is really the western boundary currents, which I've highlighted with these yellow boxes. And they are the largest sources of energy into the atmosphere on Earth. And that makes sense because the ocean circulation is bringing warm water along those currents beneath cold winter air, leading to very large turbulent fluxes that contribute energy to the atmosphere above it. You'll also notice that the northern hemisphere land masses, which are quite cold at this time of year because it's wintertime, are sinks of energy. So that's as we expect. Now looking at the southern hemisphere, where it's summertime, meaning it's the main monsoon rainfall season, we can see the three continental areas marked in the purple boxes are quite strong sources of energy into the atmosphere. This is also consistent with what we'd expect because typically we think of the heating of the atmosphere over land masses in summer as being a key part of the land-sea contrast that has been used to explain monsoons historically. But now in the northern hemisphere summer, shown on the right here, we see a surprising deviation from that pattern. The largest MSE source is over South Asia, but it's over the ocean rather than over the land. The other monsoon systems in the Northern Hemisphere, that's North America and West Africa, don't have this feature. It only occurs over the Northern Indian Ocean. And we generally think of monsoons as having their main energy sources on land, and that holds up in every case except this one, which happens to be the most vigorous monsoon on the planet. So because this feature was so striking and so counterintuitive, we verified it in as many products as we could find. I was previously showing you the NCAR CFSR product. Now you're looking at ERA 5. And you can see that the spatial pattern has changed a little bit, but that there's still this very large maximum in this quantity over the Bay of Bengal. On the right, the graph shows the net energy input averaged over the longitudes spanned by the Bay of Bengal, and the latitude of the northern extent of the Bay of Bengal is marked by the dotted line. The orange line is showing the net energy input from ERA 5, so what's on the map on the left. And the yellow envelope shows the range of values of the same quantity from 6 different reanalysis products. And you can see the peak is consistently over those latitudes of the Bay of Bengal. It's not just the reanalysis products where this feature keeps showing up. We also tried this calculation using Ceres, which is the main direct observational data set we have of top of atmosphere fluxes. And we combined it with 3 different observational estimates of air-sea turbulent fluxes. So we had sea flux from NOAA, OA flux from Woods Hole, and NOCS from Southampton. Now, while the actual value of the estimated flux varies quite a bit between these 3 products, they all have a maximum over the latitudes of Bay of Bengal. That's somewhere between 5 degrees and 20 degrees north. The reanalyses do show some variation in the spatial pattern, and some of them show higher values over the Arabian Sea than over the Bay of Bengal. But the maximum is consistently always in the northern Indian Ocean. And importantly, it's always over ocean rather than over land. So from here on, I'm going to focus on explaining this feature and understanding its implications. So everything I show is going to be averaged over the June, July, August season and focused over Asia and the Indian Ocean. So to try to understand how this local maximum arises, we decompose the fluxes into surface and top of atmosphere fluxes. Again, at the surface, which is what you're looking at on the left, that is the sum of latent, sensible, shortwave, and longwave heat flux. And on the right, you're looking at the sum of net ingoing shortwave and net ingoing longwave. I've computed both of these such that the sign is positive when the heat flux is directed into the atmosphere. So positive is upwards for the surface and downwards for the top of the atmosphere. Now, again, here we have another result that I found really quite surprising, which is that the ocean is not a net energy source for the atmosphere, but instead the net flux there is very near zero, even slightly negative. Instead, the big influx of energy comes from the top of the atmosphere fluxes that are shown on the right. Now, I thought it was really very interesting that the ocean here is not on balance providing energy to the atmosphere. My expectation was that because the Indian Ocean is generally transporting heat northwards through most of the year, and because of the well-known large latent heat flux over the Bay of Bengal during the summer, there should be a big transfer of energy from ocean to atmosphere over that region. On the right, I'm showing the an estimate of the turbulent fluxes directed upwards at this time of year from OA flux. And over the Bay of Bengal, this quantity is about 160 watts per meter square, which is quite large. But as it turns out, this is actually canceled by the downward shortwave going into the ocean. So this area is really quite different from those western boundary current regions we saw earlier, where the surface turbulent flux was the main energy source for the atmosphere. And so we had to discard our initial hypothesis that the ocean heat transport and latent heat flux were responsible for the oceanic energy input maximum. So going back to our surface and top of atmosphere flux maps, on the right, you can see that the area of strong energy input to the atmosphere over the northern Indian Ocean is approximately the shape of that maximum that we're interested in explaining. I also want to point out here that we're using the net flux at the top of the atmosphere. So this means the effects of reflection are accounted for. So when you see these sharp contrasts between the ocean and the land surface in TOA fluxes, some of that, not all of it, but some is due to albedo and other surface properties. That is, the land is reflecting some of the incoming radiation to space. So now looking more closely at the TOA flux, we split it into two components, the net shortwave and the net longwave. The net shortwave flux, which is on the left, is always positive into the atmosphere because of the insolation coming in. And the net longwave, which is on the right, is always negative because the Earth is radiating heat back out to space in the longwave wavelength range. Now, this map of long wave, interestingly, it has the lightest colors oriented over sort of a bullseye over the Bay of Bengal. And that's quite similar to the pattern of net energy input that we saw. The lighter colors indicate less negative values, meaning that there is, for whatever reason, less loss to space over that area. The main factor that affects outgoing long wave is cloud cover. Because the radiation out to space is emitted from the tops of clouds, and because the tops of clouds are quite high up in the atmosphere where it's cold, this means that less energy is emitted out to space in the presence of clouds because it's emitted from the temperature at the top of the cloud. This also means that the taller the cloud, the less energy is emitted to space, meaning that taller clouds contribute more to retaining energy within the atmospheric column. When we look at this global map of high cloud cover, and here we're using the Calypso definition, which classifies anything higher than 10 kilometers as high clouds, we find that the area covered by high clouds in the region is larger than pretty much anywhere else in the world. So to put that a little more precisely, the map is showing cloud fraction of clouds above 10 kilometers. And so that's the fraction of each grid cell that is covered in clouds taller than 10 kilometers. And that fraction exceeds 40% or so over most of the region from the Arabian Sea to Southeast Asia in the June, July, August climatology. We also confirmed using observational data that this really is associated with an extremely strong long wave forcing over the region. These are histograms of the observed climatological long wave averaged over a few areas. So the black line is showing the global tropical mean, and the modal value of that histogram is about 10 watts per meter square. The East Pacific ITCZ region is only slightly higher. And the West Pacific warm pool has a modal value of about 25 watts per meter square. We also chose another vigorous monsoon system for comparison. So we looked at the Southern African monsoon, which is shown in green. And we averaged the long wave effect there over just the summer rainy season. And while the modal value is higher, that distribution is still quite broad. Finally, we have the Bay of Bengal region, shown in blue, where the modal value is about 70 watts per meter square. This is really just about the strongest long wave effect of clouds that we see anywhere on Earth, and it's coming from that large area that was covered by very high cloud tops. The high cloud tops come from deep convective activity with typically top-heavy profiles of ascent, and the presence of a lot of these mesoscale convective systems in that area probably contributes to that. Now, to be completely honest, we don't fully understand why the convection in this particular part of the world produces clouds that have this incredibly strong long wave effect compared to anywhere else with convective activity. I'm going to leave that as a mystery to solve another day and return to the main question in this study, which is how this large oceanic maximum in net energy input comes to be. And in the past few slides, we've gone far enough to establish that the long wave effect of clouds is exceptionally strong in this part of the world, and that it's a major contributor to the net energy input to the atmosphere here. So let's take a step back and think about what exactly it is that clouds do to the energy content of the atmosphere. In the downward direction, because they reflect some of the incoming shortwave radiation back to space, they reduce the amount of incoming energy. In the upward direction, they block outgoing long wave, and as I just described, they emit less energy out to space from a cooler temperature. So effectively, both incoming and outgoing fluxes at the top of the atmosphere are being reduced by the presence of clouds. Now, when the surface below those clouds is land, because the land has a very low heat capacity, the various terms in the surface heat budget should cancel out on seasonal timescales because the land can't store heat at that timescale. So the variations in the net energy input over land really come from what's happening at the top of the atmosphere with cloud cover. Now, what happens over the ocean is a bit different. The ocean is dynamic and it has high heat capacity, so it's able to transfer heat around horizontally quite a bit, and that results in uneven surface turbulent fluxes. But in the context of radiative fluxes, there are big differences there too. So over the ocean, most, not all, but most of the incoming shortwave radiation is going to be absorbed by the ocean surface, both because of the low albedo of the ocean, meaning that there's not much reflection back from the surface of the water, and because of the high heat capacity of the water, meaning that the energy is actually absorbed and retained in the water. So unlike over the land surface, the shortwave part doesn't contribute much to the net warming of the atmospheric column. It contributes to the warming of the atmosphere-ocean system as a whole, but when you consider the atmospheric column, the shortwave radiation mostly goes straight through. Now, when cloud cover develops over the ocean, as before, it's blocking shortwave from coming in and blocking long wave from getting out. So because shortwave is relatively unimportant to the energy budget of the atmospheric column here, that negative effect through the reflection of shortwave doesn't make very much of a difference. The main effect of clouds on the atmospheric energy content here is to block the outgoing long wave, retaining energy in the column. So what this means is that over the ocean, the net cloud radiative effect on the energy content of the atmosphere is always a positive warming effect. Contrast this with what happens over land, where the surface fluxes effectively cancel out. The balance of long wave versus short wave effects can vary in different places, but the net effect is relatively small over land, and the short wave effect of clouds often wins out. What this means is that the exact same cloud cover can have opposite effects on the atmospheric energy input, depending on whether the clouds lie over the ocean or whether they lie over the land. Over the ocean, it always increases the atmospheric energy content, but over land, it can actually reduce it. So this results in a reduction of the land-sea contrast in the sources of net energy input. Another thing to keep in mind is that by retaining more energy in the column, the cloud long wave effect has the ability to invigorate the convection that generated the high clouds in the first place. And that can lead to more cloud cover and higher cloud tops. So there's potentially some sort of feedback there. And that's consistent with work that has been done by Ding Ma, Adam Sobel, and others, showing that radiative feedbacks play a very important role in the rapid onset of the South Asian monsoon. So over the South Asian region, the large energy input to the atmosphere over the ocean is strongly influenced by cloud cover, partly because this is one of the locations with the strongest cloud long wave effect on the planet. The effect of the net energy input to the atmosphere is more pronounced over ocean than over land, and that's because the shortwave effect is much less important over the ocean than it is over land. In most places around the world, this just results in a reduction in the land-sea contrast, but over South Asia, the effect is so strong that it actually reverses the direction of the land-sea contrast, and it gives us a stronger energy source over the ocean than over land. So to summarize our results thus far, we saw that the net energy input to the atmospheric column, or NEI, is a good predictor of shifts in tropical precipitation. So we looked at the global distribution of this quantity, and we found that while most monsoon regions have a local maximum or energy source for the atmosphere over land, this is not the case over South Asia, which is a very surprising and counterintuitive result. Then we examined the components of the NEI, and we concluded that the long wave cloud radiative effect was the key contributor in this region. And we attributed this to the very large high cloud fraction over the area in the summertime. So this now brings us to the second part of the study. Now that we've established that the cloud cover is an important region for the energy source over the ocean, we wanted to understand the implications of the presence of that energy source and of the large long wave cloud radiative effect and their impacts on rainfall over the whole region. So to begin to answer this question, we ran a suite of experiments where we eliminated cloud radiative effects. That is, we made the clouds in the model transparent to both long wave and short wave radiation. We used CESM2 with a full 32 level atmosphere and a slab ocean. For those of you familiar with this model, this was the scientifically validated e-test component set. We ran our experiments at the standard resolution of the CMIP runs. Our slab ocean was 30 meters deep with a climatological heat flux that represents the effects of ocean heat transport. And we used a standard land model with climatological vegetation and kept our atmospheric chemical composition constant at 1850 levels of greenhouse gas and of aerosols. So the way we designed our experiment was to run an ensemble of 5 separate experiments where we switched off the cloud radiative effects. And each of those 5 had a small initial perturbation. The experiments were all started on the 1st of May after a 5-year spin-up, and we analyzed results only from the months of June, July, and August. The reason for that design was that we wanted to avoid model drift. Now remember that we're making quite a dramatic change to the model physics. In many previous studies, like in the cookie ensemble, for example, the climatological cloud radiative effect was retained and the deviations from that were analyzed. But in this ensemble, we really just go in and set the cloud radiative effect to 0. So in this world, it might be raining, but while it's raining, the sky is still blue. So such a drastic change can lead to drift in the model, and we wanted to avoid those effects. So we examined only the 3 months after the experiment started. We also only made this change within the tropical belt because we didn't want to introduce any major extratropical changes, which, as we saw in the beginning of the talk, can result in shifts of the ITCZ, and they can also set up very unrealistic equator to pole gradients, which might interfere with interpreting our results. Our control run that we compare our experiments to was also an ensemble designed in the same way. So 5 years and 4 months of spin-up, after which we initiate 5 branches on the 1st of May. And the only difference here was that we let the model simulate cloud radiative effects as usual prognostically. So then this way we have these 2 ensembles between which we can make an apples to apples comparison. So now here is what the net energy input looks like in the control run of this model. We see a very large maximum over the northern Indian Ocean, and as in the observations, the oceanic MSE source is larger than the land MSE source. You may have noticed that here the largest values are over the Arabian Sea instead of the Bay of Bengal, but this is not far from the range of variation we saw between different reanalysis products. The really important thing here is that the NEI maximum is oceanic, and so our land-sea contrast in NEI is in the correct direction and has the correct magnitude. The other important thing is that the net cloud radiative effect looks very similar to the reanalyses. So on the left is the JJA clear sky minus all sky top of atmosphere flux from ERA 5. And on the right is the same in the control run. So globally, that pattern looks really quite similar. The magnitudes are about right. And importantly, the maximum effect is over the South Asian region. So now let's start looking at the difference between the control and our experiments. So now throughout this talk, I'm going to use control, which is the ensemble that has the cloud radiative effects, minus the experiment, which has the transparent clouds or no cloud radiative effect. So I know that typically we go the other way around where you do experiment minus control, but here it becomes a little simpler to understand if we think of the experiment with no clouds as some basic state, and the control as the effect of clouds applied to that basic state. So that way, any differences I show will correspond to the effect that clouds have on the climate. So here, this is the precipitation difference with green shading showing where it's wetter when we add clouds, and the brown showing where it's drier when we add clouds. So a few things about this stand out immediately. First, the biggest changes are near where the maximum rainfall typically occurs. So you'll see that the purple contours, which represent rainfall greater than 5 millimeter per day in the control, are generally surrounded by the deepest shades of green and brown. So it looks like the main changes are spatial shifts of the rainfall maxima. So for example, if you look over the East Pacific and the Atlantic ITCZ, you can clearly see that there's a northward shift of the rain band. And that's consistent with earlier work on aquaplanets, where people have shown that cloud radiative effects shift rainfall deeper into the warmer hemisphere. And in this case, because we're looking at summer, the northern hemisphere is the warmer hemisphere. But as you've probably noticed, the spatial pattern over Asia is a little more complicated. And one of the main features there is a shift from northeast to southwest, where rainfall reduces over much of China when you add clouds, and it increases over peninsular India and the surrounding ocean. Now, to explain these shifts, we're going to look first to the change in net energy input, which I'm showing on the right. So you can see that over the entire northern Indian Ocean, the net energy input goes up in the presence of clouds, but over land, it's reduced. So that's what we expect from our earlier analysis. We think that the presence of clouds over the ocean increases the amount of energy supplied to the atmosphere there. You might have also noticed that this spatial pattern looks quite different from our map of cloud radiative effects, and that is to be expected because in those earlier maps, we were just doing a subtraction to get the estimated radiative effect. But here in these experiments, we're allowing the atmosphere to respond by changing its circulation patterns. So there are those dynamical adjustments in response to the absence or presence of clouds that are in this pattern. So now I'm going to interpret this result in energetic terms, that is in the framework using the flux potential that was developed by Bill Boos and his co-authors, which I outlined at the beginning of the talk. After I do this, I will also show you a more conventional dynamical interpretation of the results, and we'll see that they both give the same result. So here now I'm showing the June, July, August change in precipitation. Again, this is with clouds minus without clouds. I've marked the location of maximum rainfall in the control, the experiment, and the observations. So you can see that the control does a pretty good job of getting the location of the maximum precipitation, so along the Malabar coast. But in the experiment with transparent clouds, the maximum is really quite far away, and it's over southwestern China. So the spatial pattern of rainfall in that setting is really going through some dramatic change. And the addition of clouds drastically dries out that southern China area. If you look at the color scale, that reduction is about 10 to 15 millimeters per day. And on the other hand, the increase over the west coast of India is about 6 to 12 millimeters per day. Now, if we look at the zonal centroid of precipitation, that is the centroid of precipitation at each latitude in the experiment and in the control, we see a displacement of the centroid from the east in the experiment, that's the pink line, towards the west in the control, which is the blue line. And the shift is particularly pronounced over the oceanic part of the domain. Over the full domain, the average shift is about 4.3 degrees towards the west when we add clouds. And now I've added two more lines, these dashed lines that represent the energy flux prime meridian, that is the zero line of zonal energy transport. This line also shifts from east to west with the addition of cloud radiative effects. The shift in that line is about 5.8 degrees, so it's of a similar magnitude and in the same direction as the rainfall shift. This is because the inclusion of clouds increased the input energy to the western part of the domain, which is more oceanic, and reduced it to the inland eastern part of the domain. So by adding clouds, we effectively induced an east-west energy gradient here, which the circulation is trying to counteract by transporting energy eastwards. Now, we can also consider these results from a dynamical perspective, which can give us an explanation that's more in line with the existing literature and which can help us contextualize the result. So before I get into that, I'm going to briefly review the Rodwell-Hoskins mechanism, which is an important theory relating to the monsoon circulation over Asia that's quite relevant here. So the Rodwell-Hoskins mechanism was first proposed to explain why Western Asia is so much drier than Eastern Asia, especially during the summer months when the Asian monsoon is at its most active. So to study this, the authors imposed an off-equatorial heat source, which is indicated here in red, and showed that this produced a typical gill response in the troposphere. That is, a pair of Rossby gyres to the west and an eastward propagating equatorial Kelvin wave to the east. Because that heat source is off-equatorial, you get a meridionally asymmetric response with the large Rossby gyre in the north and a smaller one in the south. The Rossby gyre is oriented in a way that induces subsidence to the north and the west of the original heat source. This shows a result and a schematic from a subsequent study that simulated this in an idealized rectangular continent. So that's marked by the two dashed lines. The upper panel shows the pattern of rainfall that develops over the continent. And you can see there that the rainfall is very intensely concentrated towards the southeastern corner of the northern hemisphere. The Rossby gyre is located to the northwest of that rainy region, and this causes the subsidence of dry air there. And because the winds are also oriented in a way that brings cooler mid-latitude air into the continent, that means that air with much lower MSE content is directed into the continent from the west. Then that cooler, drier air ventilates the western part of the continent, and it makes it more difficult for convection to occur there. So it really squeezes the area where convective precipitation is possible towards the eastern edge of the continent. So now applying that thinking to our experiment, this is what the June, July, August precipitation field looks like in the experiment with our transparent clouds. I'm sure you're all familiar enough with the pattern of rainfall over the region to see how hugely different this is. The rainfall is very tightly concentrated to remain in the southeastern part of the Asian continent. So now looking at the advection of MSE over the region, you can see a large area of negative MSE advection, which is shown in shades of blue on the western half of the domain. This is associated with the northerlies in the top left corner, showing the effect of transporting that low MSE air from the mid-latitudes into the domain, which is exactly what you expect to see in the Rodwell-Hoskins mechanism. And just to highlight how dramatic of an effect that has, here I'm showing the MSE itself at that same level in the experiment on the left and in the control on the right. So these obviously look very different. One major difference is that the MSE overall in the experiment is lower. And that's partly because without clouds, a lot more energy is lost to space. But beyond that, the spatial pattern is also quite different. And you can see that there's a stronger east-west contrast in MSE in the experiment that's on the left, where the ventilation by the cooler and drier mid-latitude air is playing a big role in the MSE content of the western half of the domain. I also want to emphasize that the circulation response that we see is very important to the response in rainfall. So here on the left, I'm now showing the difference in surface turbulent fluxes with and without clouds. So over land, the presence of clouds results in a huge reduction of the upward surface heat fluxes. And that's because in the absence of the cloud radiative effect in the shortwave, the surface becomes very hot. And that leads to large upward surface turbulent fluxes that counteract that heating. Now, on the right, I'm showing the vertical temperature profiles averaged over two boxes. So the blue line is what I'm calling South Asia, and it's averaged over the blue box. And the orange line, which I'm calling Southeast Asia, is averaged over the orange box. And in both cases, adding clouds cools the surface. It also warms the upper atmosphere by retaining some of the heat there. So according to this, clouds should have a stabilizing effect. That is, if we thought only about what happens in the vertical dimension and ignore the circulation changes. But if we look at what actually happens, we see that there's a strong destabilizing effect of clouds on the MSE profiles over South Asia. And this comes about mainly because of the circulation changes and the dry air advection that I was showing earlier. So here now I'm showing the change in MSE profiles over South and Southeast Asia. South Asia is in blue, Southeast Asia is in orange. And again, this is the control minus the experiment. So this is showing the effect of adding clouds. In both cases, the values are all positive, meaning that clouds are increasing the MSE in general. And we saw that earlier in the maps of MSE that I showed. And this is related to clouds keeping more of the energy within the atmospheric column and preventing its release to space. But now in terms of the actual vertical structure, the addition of clouds over South Asia increases the MSE more strongly in the lower troposphere than in the upper troposphere. And this is coming from the advection of MSE, because when we don't have clouds, there's advection of low MSE air into this area. And when we add clouds, that doesn't happen. So South Asia is able to remain warm and moist under the circumstances where you have clouds. Now looking at Southeast Asia instead, while there is an increase in the MSE in the column, you can see that this is a stabilizing increase because the increase is smaller at the bottom of the troposphere than it is higher up. So that change in circulation is giving us opposite effects in the two regions. And that's reflected in the profiles of vertical motion, which I'm showing on the right. There's an increase in ascent over South Asia. So on this graph, the negative values show upward motion, and you can see enhanced ascent in the blue line representing South Asia. Meanwhile, the ascent is suppressed over Southeast Asia, which is shown by the positive values along the orange line. So that circulation change is really crucial to understanding how the precipitation should respond to the absence or the presence of cloud radiative effects. Now, I'd like to quickly synthesize what we learned from the two different frameworks for interpreting our results. In the dynamical framework, we saw that in the absence of clouds, Asia behaves somewhat like an idealized rectangular continent that quickly develops a pattern of maximum rainfall over the southeast corner. That happens because of the advection of low MSE air that arises from the Rossby Gyre. And when we add cloud radiative effects, we stabilize the column over land, which reduces that negative MSE advection by weakening the Rossby Gyre. And that therefore establishes a large region of high MSE over South Asia, and therefore convection is able to develop there. Now, in the energetic framework, what happens when we add cloud radiative effects to the system is that we are effectively adding an east-west asymmetry in the net energy input. So that's that first map there. We're reducing the energy input over land and increasing it over the ocean. And the circulation, which from the dynamical framework, we know that that's transporting negative MSE towards the east, shifts to compensate for that. So the zero line of energy transport shifts towards the west. And that, as expected, results in a shift in the center of mass of precipitation shown on the right. So both of these frameworks here are in agreement and are just different ways of arriving at the same result. Before wrapping up, I also wanted to briefly touch upon some of the interesting effects we saw on a global scale beyond tropical Asia. So as I was pointing out to you earlier, clouds act to reduce the energy sources over land and enhance them over the ocean in the summer hemisphere. We also see an associated reduction in precipitation over the monsoon land regions when we add clouds. So on the whole, we find that the total proportion of rainfall occurring over land increases when clouds are removed. And that increase is by about 25%. So something new and general that we've learned from this study is that clouds act to shift rainfall more towards the ocean globally, because cloud radiative effects have different impacts over land and over ocean. And this can have some pretty important implications. The main implication is that when we study effects of clouds on rainfall, we need to be really accounting for the difference in heat capacity at the surface. Here's a list of several key global studies of rainfall and cloud radiative effects in models. All of them either use aquaplanets, meaning that they don't have that spatial variation in the surface heat capacity, or they use imposed SSTs, meaning that they don't account for the heat capacity of the ocean at all. In our literature review, we weren't able to find any experiments that accounted for this important difference in the heat capacity of land versus ocean, meaning that all of our theoretical knowledge of how clouds affect rainfall in models comes from studies that are not able to capture that shift from land to ocean that occurs because of clouds. This is particularly important because clouds are such a major source of uncertainty in our climate models, and therefore in our climate projections as well. So this is a major gap, and we really need to start having experiments that account for the difference between land and ocean heat capacity while studying clouds. So to summarize, we began with a fairly surprising result, which is that the maximum in net energy input to the atmosphere is over the northern Indian Ocean rather than over the land. And that runs counter to the way we've thought about land-sea contrast in monsoons for really centuries. So we analyzed fluxes to understand how this oceanic maximum arises. And we found that clouds play a key role, particularly the strong long wave effect of the very high clouds in that region. And to understand the implications of this, we ran experiments where we eliminated the effects of clouds. And in those experiments, we saw a large zonal shift over South Asia. In the absence of clouds, the Asian monsoon would be entirely concentrated in the southeastern corner of the Asian continent, by which I mean over southern China and Southeast Asia. And the addition of clouds is really what centers that Asian monsoon rainfall over the Indian subcontinent. We looked at this explanation using two different frameworks. The dynamical framework, which pointed to the advection of dry air as a central factor, and an energetic framework, according to which the zonal shift of the maximum net energy input results in a corresponding zonal shift of precipitation. And finally, we also found the important result that tropical clouds in general act to shift rainfall away from continents and towards the ocean. These results were published recently in GRL, and the reference to the paper is here at the bottom of the slide. So this work has raised a number of questions, some of which I've listed here. The first is that we don't really have a satisfying explanation for why the long wave effect is so much higher over South Asia than anywhere else. The high cloud fraction here is larger than anywhere else, which is related, but I can't really say we know why that occurs. Another question is what impact aerosols have on all of this. We kept aerosol concentrations constant between our two experiments just for simplicity, but aerosols are quite important in this part of the world, and they must both directly affect the net energy input through absorption and reflection, and also indirectly affected by changing the cloud cover itself. We also don't know what the changes will look like under global warming, where cloud cover may change in a number of ways, which would end up changing the pattern of net energy input and therefore rainfall. So I'd like to leave these questions up on the screen while I answer your questions. And thank you once again for having me.
Thank you, Dr. Nandini. Are there any questions? Please put your hands up. Or she can go look at the chat box. Chetan.
Thank you, Nandini, for this interesting talk. I have a clarification. I want to you to clarify this thing. In the beginning,
Okay.
you said that net energy flux or change in heat sources in northern hemisphere and southern hemisphere leads to shift in ITCZ and precipitation.
Yeah.
And later on, I got the feeling that you are trying to suggest deep clouds in Bay of Bengal are the cause of NEI to be high over Bay of Bengal. So I find this slightly contrasting. Can you please clarify whether it is NEI that causes change in precipitation or deeper clouds, or it is the other way around, that precipitation and clouds are responsible for NEI?
Okay, so this is I think I understand the confusion that you're talking about. And one thing to keep in mind is that this is a diagnostic explanation. It's not really explaining which happened first. So it's not a perfectly causal explanation, but so in the case of the ITCZ studies, that was definitely causal because, you know, the authors of those studies were deliberately putting a heat source in one of the hemispheres. So then you knew that that was causing the shift in the ITCZ. But in the real world, it's much harder to diagnose which of those two things happens first. Does that help explain?
Okay, thank you. Maybe I can discuss this further later.
Okay. I guess what I'm trying to say is just that they aren't contradictory, because the clouds are affecting the NEI, and of course the clouds are also related to the precipitation, right?
Yeah.
But because of feedbacks between these things, we've not actually teased it apart in a causal sense, and it's just a diagnosis of the balance.
Yeah. Okay. Yeah.
I hope that helps.
Professor Devra?
Thanks.
Devra, are you there? Please unmute.
Yeah, I'm Devara from MIT University, Haryana. Really, I'm excited by the lecture by Dr. Nandini Ramesh. Really, it is quite inspirational, and then I have two fundamental doubts. One is, all along, she has been explaining about the model output, model results. I don't know how much extent these model outputs or model results are validated with experimental observations. That's number one. Number two is, even if it is in the absence of clouds or presence of clouds, of course, and due to the albedo over oceans is very low, as you said, I feel a lot of aerosol particles are being transported from land over the oceans. So in that case, you said that one or two places you have switched off the aerosol effect and then computed your models or run the models. I don't know to what extent that sort of results will coincide with the real information. That is number two. And of course, you have already before exactly I wanted to ask this aerosol scattering as well as absorbing aerosol impact on the precipitation enhancement, what you have observed over oceans. Of course, you have already listed as second question in your list of questions. So that I wanted you to elaborate a little more. So what way actually the aerosols, it is a very complex problem, and what sort of aerosols ultimately you found over oceans directly, or what sort of aerosols they are transported from land to our oceans. Actually, these are the things which really depend upon the enhancement of precipitation what we have observed over oceans. But of course, I feel all the time it is not that shift of rainfall from land aerosols to ocean. Otherwise, also possible what I feel. Of course, that is to be thought over in that aspect. But I feel all the time need not be ocean over ocean's rainfall or this precipitation is maximum compared to the land. So transport makes the real link. We know that. But of course, transport alone cannot answer this question. Transport, what sort of aerosols are being transported? And also the gas to particle conversion. I wanted to make out here. Of course, you uttered about the gases. Of course, there is a complex phenomena called gas to particle, which plays a lot of role in the cloud related to forcing. So there are so many parameters. But I surprised once you switch off the clouds. I don't know what sort of information your model gives. Of course, I am not expert in models, but I feel very happy if you explain these aspects. Thank you.
Okay, thanks. So I'll go to your second question first, which is that where we don't switch off the aerosols, we keep them. And so they're the usual concentrations that are specified for pre-industrial runs in climate modeling scenarios. And we don't switch them off, but we don't change them between the experiment and the control. So we're not really looking at the effect of changing the aerosols at all. And as for validation, I did show you several maps of the relevant variables earlier on, comparing the model and the reanalyses. In general, this particular version of CESM has been used to study monsoons and is thought to be one of the models that does better. And about your question on the question that I have up on the slide, what if what effect the aerosols have on the NEI is, I mean, it's very difficult to answer without actually performing a study of this. But if you're happy for me to conjecture, I would think that aerosols like black carbon, which have the effect of absorbing heat and therefore increasing temperature, are likely to end up warming the column, so increasing the net energy in the column. And probably things like sulfates, which cause reflective, have reflective properties in the short wave, are going to probably have a cooling effect and therefore a reduction of the net energy input. And that's very simplistic, and it's just a guess. And honestly, the really complicated part of this would be how those aerosols interact with the nature of the clouds themselves. So they can change the radiative properties of clouds, and then that would indirectly change the net energy input. So that's as far as I've thought it through, to be honest. I don't have more than that, and I don't think I can usefully say anything more without doing an actual study of that.
Thank you so much, of course. Thank you.
Any other question? Anybody else? Shrikar, is anybody on chat box? Any questions?
Right now, I don't see any questions on chat box.
Okay, fine. So, so let me just conclude this seminar by thanking Dr. Nandi Ramesh for giving a very, very lucid presentation. And so for many of the students in the audience who may not be aware of the energetics approach, which is somewhat new, this was a very nice exposition. And you have also raised many new interesting issues in relation to aerosol and others. And so we look forward to more work from you in this area. Thank you very much.
Thank you. Thanks again for having me.
Yeah. Okay, we conclude the seminar at this point.